I welcome all of you to the class 12th chemistry class, and let us revise what we have studied yesterday. Yesterday we studied about the chemical properties of aldehydes and ketones. So far we have started studying, or we know that these aldehydes and ketones being or having the carbonyl group, they shows the nucleophilic addition reaction or addition reaction mostly they shows. So since aldehydes and ketones both possess carbonyl functional group, they undergo similar chemical reactions. First, we want to study about the nucleophilic addition reactions. So aldehydes and ketones undergoes nucleophilic addition reaction. They both undergoes the same type of nucleophilic addition reaction. So let's have a look to this. You can pay attention. Here you can see that this is the carbonyl group where the nucleophile has attacked. This carbonyl carbon is sp2 hybridized. As this carbonyl carbon is sp2 hybridized, you can see that the shape of this is planar. All the bonds which are sp2 bonds, that means they are available in the same plane, and you can see that there is a slight positive charge on carbon and slight negative charge on oxygen, because oxygen is more electronegative, whereas carbon is less electronegative. So as it is less electronegative, you can see that there is a charges or small charges being generated. So this bond become polar. So nucleophile, which is a electron rich, as the carbon, as the nucleophile is electron rich, it generally attacks on the positively charged carbon atom. This is how the nucleophilic reaction starts. As the nucleophilic reaction starts, my dear students, in a reversible first step, which is a slow step, nucleophile combines with the carbon. So the hybridization of this carbon, which was sp2 initially, it simply turns into sp3. So as the hybridization changes to sp3, the shape of compound turns out to be tetrahedral, which is an intermediate that we got because still there is a negative charge on oxygen. This way, a tetrahedral shape is being generated. Now, my dear students, as the tetrahedral shape is there, uh, the oxygen still has a negative charge. So, in a fast second step, H plus combines with oxygen and gives us the final addition product, which contain carbon bonded to the nucleophile and the oxygen bonded to the hydrogen to gives us the hydroxyl group. This is how, my dear students, we understand about the mechanism of the nucleophilic addition reaction into the carbonyl compounds, especially the aldehydes and ketones I am talking about. Now, when a nucleophile attack the electrophilic carbon atom of the polar carbonyl group from a direction approximately perpendicular to the plane of sp2 hybridized orbital of carbon atoms, the hybridization of carbon changes from sp2 to sp3. In this process, and a tetrahedral alkoxide intermediate is produced. This intermediate captures a proton from the reaction medium to give us the electrically neutral product. So the final product, which is in which the carbon is bonded to nucleophile, and oxygen is bonded to hydrogen. This is the electrically neutral product we get. The net result is addition of nucleophile and H plus across the carbonyl carbon double bond as shown in the figure. Now, my dear students, we need to understand the reactivity. When we understand the reactivity, we understand the reactivity in two manners. The first manner is the reactivity that is based on the steric reasons, and the second one is electrical. So here we try to compare the reactivity of aldehydes and ketones. So we try to understand the comparison or reactivity of aldehydes and ketones in comparison with each other. We find that aldehydes, aldehydes and ketones aldehydes are more reactive generally than the ketones in nucleophilic addition reaction due to the steric and electronic reasons. So first, let us look at the steric reason. Sterically, the presence of two relative large alkyl group in ketones hinders the approach of a nucleophile to the carbonyl carbon than in aldehyde having only one such a substituents. And electronically, my dear students, aldehydes are more reactive than ketones because two alkyl groups reduces the electrophilicity of the carbonyl carbon more effectively in ketone. So, you know, alkyl group are electron donating group, and that is why they reduces the electrophilicity by providing more electron density to the carbonyl carbon. So more is the number of alkyl group, less would be its reactivity, and that is why the ketones are less reactive as compared to the aldehydes. Now the next point is, would you expect benzaldehyde? You know, benzaldehyde is having an aromatic ring with it instead of the alkyl group. So benzaldehyde is this ARCHO, or you can say C6H5CHO. So would you expect benzaldehyde to be more reactive or less reactive in nucleophilic addition reaction than propanol? And we need to explain our answers. So let's have a look to this. The carbon atom of the carbonyl group is in carbonyl group of benzaldehyde is less electrophilic than carbon atom in the carbonyl group present in the propanol. You can see here that the carbon atom bonded to the aryl group, the electron comes here and it turns into the double bond, and you can see that these are the two resonance structures that takes place. The polarity of the carbonyl, the polarity of the carbonyl group is reduced in the benzaldehyde due to the resonance as shown above, hence it is less reactive than propanol. So, my dear students, as compared to the propanol, propanol is this. CH3, CH2, CHO is a propanol. So propanol has got C double bond O. One side it has got H, another side it has got CH3, CH2. Both these are electron donating group, and ultimately the electron density on carbon increases, so the positive charge is also in comparison with the ketone decreases, but here the electron present undergoes the resonance, and that is why the benzaldehyde is less reactive than the propanol. Some important examples of nucleophilic addition and nucleophilic addition elimination reaction. So we are now going to study few very important examples. First, addition of hydrogen cyanide HCN. Let's have a look to this. Aldehydes and ketones react with aldehydes and ketones react with hydrogen cyanide HCN to yield cyanohydrines. This reaction occurs very slowly with the pure hydrogen cyanide. Therefore, it is catalyzed by the base and generated CN minus. So let's first look at the reaction that takes place. Cyanide ion, being a stronger nucleophile, readily adds to the carbonyl compound to yield corresponding cyanohydride. First, the reaction is done in the basic medium, so you can pay attention here that HCN in the presence of base produces the cyanide ion, which is a nucleophile. This cyanide ion attacks on the carbonyl carbon. Why does it attack on the carbonyl carbon? Because carbon has got slightly positive charge, and thus it produces the tetrahedral intermediate. In the presence of H plus, this tetrahedral intermediate turns into a compound that contains both CN group and OH group, which is collectively known as a cyanohydrine. So this is how we get cyanohydrine. Let us study the same with some example. Cyanohydrines are useful synthetic intermediates. So if we have methanol and HCN, we get methanol cyanohydrine. If we have ethanol, this is what it is, your ethanol. So if you have ethanol and HCN, you get ethanol cyanohydrine. If you have benzaldehyde, that reacts with HCN, it gives us the benzaldehyde cyanohydrine. If we have ketone like acetone reacts with HCN, it gives us the acetone cyanohydrine. There is not much big difference that takes place. Just instead of this O, here we get OH and here we get CN. This is the product that we get, and this is how we get the cyanohydrine. Remember that these cyanohydrines are very important reactive intermediates. Now, my dear students, we are going to study the addition of sodium hydrogen sulfide. Remember, I am talking about sulfite here. So you need to remember that there is a difference in sulfate and sulfite. Sulfite is SO3 minus 2. So sodium hydrogen sulfide is your NaHSO3. Please remember this, that we are going to study here about NaHSO3. Let us understand the topic in detail. Let's pay attention. Yes. Um, Addition of sodium hydrogen sulfide. Addition of sodium hydrogen sulfide to aldehyde and ketone give addition product. You can see this carbonyl group, which may be an aldehyde or a ketone. It reacts with sodium hydrogen sulfide and it gives us the addition product. So first we get such an intermediate. O is bonded with Na and the another carbon bond goes with the OSO2H. That is nothing but your SO3H. Now again the proton transfer takes place. Let us see how the proton transfer takes place, my dear students. So as the proton transfer takes place, you can see here the hydrogen comes to oxygen and sodium goes to the SO3. Ultimately, we get bisulfite addition product due to the proton transfer. We can have hydroxyl group bonded to the carbon and SO3Na group bonded to the another to the same carbon, and this is how the bisulfite product is produced. If we want to write SO2 here, then we should write O here. So we can write OSO2Na or SO3Na, whatever it is. Bisulfite addition compound, or this bisulfite addition compound, what we get is a crystalline compound, and as it is a crystalline compound, it must be water soluble. So this bisulfite compound that we get is water soluble compound. Let us see how it is useful, or why do we prefer this reaction. The position of the equilibrium lies largely to the right hand side for most of the aldehydes and to the left hand side for most of the ketones. Now let us again understand what does this statement tells us, or what is the meaning of this particular statement. The reaction, this equilibrium, what I'm talking about, is this, that we have a particular equilibrium. You can see here that there is an equilibrium both the way. This equilibrium, if we use aldehyde here, then we get more product. So equilibrium shift towards the product. But if we use ketone, my dear students, then we get, or we always have the equilibrium shifted towards the left side, that is the reactant side. So whenever the reaction of sodium hydrogen sulfide is done with the ketone, it gives the very less yield of product. This is what it happens. But when it comes to aldehyde, it gives a good amount of product. So my dear students, whenever we have the mixture of aldehyde and ketone, suppose we have the mixture of aldehyde and ketone here. So the mixture of aldehyde and ketone, generally, it is, if we have the mixture of both, if we have the mixture of both of them, what happens? Aldehyde gives this product and ketones do not give this product. So by process of filtration, we can separate them. So we use the process of filtration to separate aldehydes and ketone. At the same time, if there are impurities in aldehyde mainly, if aldehydes have got some impurities, even in that case, these impurities can be converted, or the impurities will not react with NaHSO3, but this bisulfite, but aldehyde will give bisulfite addition compound, and that is why the impurities may also be separated. So this is how the reaction with the bisulfite can be used for the uh, purification as well as for the separation of aldehydes and compounds with each other. In other words, we take aldehydes, allow it to react with the sodium sulfide, we get bisulfide addition compound, and the product yield is good. The product yield is good when there is, the reactant is aldehyde but not the ketone. But in case of ketone, my dear students, let's see what happens, that in case of ketone, as ketone has a two alkyl group, addition of sodium sulfide is difficult, and product is obtained in product is not obtained in a good yield. So the yield of ketone that is produced is not good. You can say almost zero or very less. Thus, if there is a mixture of aldehyde and ketone, the constituent can be separated using this method. Bisulfide addition compound obtained is a crystalline compound, water soluble compound, and can be converted back to the original compound by treating the bisulfite with the addition compound with dilute mineral alkali or dilute mineral acid. So this compound can be again converted back to the aldehyde and ketone, or especially aldehyde, by mineral acid or by mineral alkali. Thus, if aldehyde compound has some impurities, so if there are some impurities, if aldehyde compound has some impurities, these impurities does not react with the sodium hydrogen sulfide, but aldehyde give water soluble bisulfite addition product, which by filtration can be separated from impurities. Thus, reaction with bisulfite is used for the purification, remember, of the aldehyde, and this is also used for the separation of aldehyde from the ketones. Now, my dear students, we want to study about the addition of alcohol. So before we move to the addition of the alcohol, I would like to ask my dear students that do you understand everything? Do you have any doubt? If you have any doubt, you can ask me. If something you could not understand, you can ask me, or you simply say, sir, understood. Please reply so that we can move forward, or I
Sir,
can.
understood.
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 Sir, understood.
Thank you, dear students, for your generous replies, and I'm so happy to, I'm so happy that you have understood everything. Let's move forward and discuss the other topics that we want to discuss now. Uh, let's move forward. Yes. Now we want to study about the addition of alcohols. So let us try to study about the addition of alcohols. Let us move forward and study the addition of alcohol. Alcohols are being added to aldehydes and ketone, and let us see how these alcohols can be added to the aldehydes and ketones. Let us try to study that. It would be wonderful if we can remove this from our screen because it is creating trouble to me. Let me try to remove it as soon as possible. Dear students, can you see what I am sharing with you? जो मैं शेयर कर रहा हूँ वो आपको
Yes,
दिख
sir.
रहा
Yes, sir.
Yes, sir.
है? Okay. So now let's move and
Yes, sir.
thank you. Now let's move and understand the addition of alcohols. आपको बीच में ये प्लीज मूव विंडो भी दिख रहा है क्या?
Yes, sir.
That is what it is troubling me. Okay. Aldehyde. Thank you, Mayur. You can please remove this. Okay. Aldehyde reacts with one equivalent of monohydric alcohol. Aldehyde reacts with one equivalent of monohydric alcohol in the presence of uh, dry hydrogen chloride to yield alkoxy alcohol intermediate called hemiacetal. Now let's look at this. Let me explain this to you once again. Aldehyde reacts with one equivalent of monohydric alcohol. In monohydric alcohol means alcohol that is having only one OH group or one hydroxyl group. The alcohol that has only one hydroxyl group is known as a monohydric alcohol. So it reacts with the monohydric alcohol in the presence of dihydrogen chloride to yield alkoxy alcohol. This alkoxy alcohol itself is known as the hemiacetal, which further react with one more molecule of alcohol to give gem dialkoxy compound. Gem means dialkoxy part is bonded with the same carbon, that is why it is known as gem. Here gem means geminal. We have seen vicinal and geminal. Geminal means on the same carbon. So it's geminal dialkoxy compound which is called the acetal. So here my dear students, we are going to study about the preparation of acetal by the reaction of aldehydes with alcohol in the presence of dry HCl gas. So now let us understand this method or by the reaction of the preparation of the acetal and hemiacetal. First we take an aldehyde. We allow it to react with the monohydric alcohol which is known as R-OH in the presence of dry HCl gas. Remember that this HCl gas must be dry. It should not having any moisture. So with the dry HCl gas, we get hemiacetal. How? You can see that this R is already present. Then we have CH. Then we had O. This O combines with the H of ROH and this R-O combined with the same carbon. Again, when this R-OH combines with the H plus, my dear students, in the presence of an acid, again this R-OH or alcohol, monohydric alcohol, reacts with this hemiacetal. The OH group or the H hydrogen of the OH group is replaced by the alkyl group OR dash, or you can say the OH group is replaced by the OR dash group and we get acetal. Hemiacetal means half acetal. Acetal means complete acetal or full acetal. So this is how, my dear students, from aldehyde we can get first hemiacetal or then we can get the acetal. Let us understand the same reaction by looking at some examples. If we have acetaldehyde and we allow it to react with the methanol in the presence of dry HCl gas, we get acetaldehyde methyl hemiacetal. So you can see that CH3CH has got OH and OCH3. But again, if we allow it to react with methanol, we get acetaldehyde dimethyl acetal. You can see that we have dimethyl acetal. So this portion we are going to call it as an acetal, and this is dimethyl acetal because it has got two methyl group bonded to it. Same way, if we have formaldehyde and if we allow it to react with the methanol in the presence of the hydrochloric acid gas, we simply get methyl hemiacetal of formaldehyde. So here, this is what it is, the methyl hemiacetal of the formaldehyde. You can even represent this compound in this manner. You can write it this way, my dear students, that you have H, then O, this is your CH2, and then you have OCH3. The same compound can be written in this manner, and this is what it is known as the methyl hemiacetal of formaldehyde. So now I hope, my dear students, this is well understood to you. Let's move forward and understand some other reactions. Ketones. We have seen that aldehyde reacts with the alcohols, but ketones also react with the alcohol. Ketone reacts with ethylene glycol. Ethylene glycol is your CH2, CH2. It's a dihydric alcohol. You have OH on first carbon as well as on the second carbon, which is known as the ethylene glycol. So this is your ethylene glycol. This ethylene glycol reacts with the ketones and gives us the ketal. Ketone reacts with the ethylene glycol in the presence of dry HCl gas and forms cyclic product known as the ethylene glycol ketal. So let us see how this ethylene glycol ketal really works. Dry hydrogen chloride protonates the oxygen of the carbonyl compounds and therefore increases the electrophilicity of the carbonyl carbon, facilitating the nucleophilic attack of the ethylene glycol. You can see here that this is the ketone that we use. This ketone, when it reacts with the ethylene glycol, in the presence of dry HCl gas, we get a cyclic compound. You can see here the cycle of 5 atom ring. So we get a cyclic compound which is known as the ethylene glycol ketal. So this is how, my dear students, we understand the ketal. Ketal, we call it ketal because it has got the ketone that reacts with the alcohol. Let us understand the production of ketal with one example. Suppose we have hexane 3-ol. This hexane 3-ol has 6 carbon. You can see here, my dear students, the first carbon, second carbon, third, fourth, fifth, and sixth. This carbonyl group again combines with the ethylene glycol to gives us the ethylene glycol ketal or ethylene ketal of the hexane 3-ol. So this is how we understand the various examples. These are the examples from your textbook exercises, my dear students. Please note this, that acetals and ketals are hydrolyzed with aqueous mineral acid to yield corresponding aldehydes and ketones. So this acetal or hemiacetal, whatever we have got, if we allow them to react with the aqueous mineral acids, we will get the respective aldehyde and ketone back from the acetal, hemiacetal or ketal or ethylene glycol ketal. So this is how, my dear students, we understand the various topics today. In the tomorrow's class, we will study about the action of ammonia and its derivative on our carbonyl group or aldehydes and ketones. So that is what we can understand in our next class. Let us revise today whatever we have discussed during the class. Let us go for a good revision of all the things that we have studied today. We have seen, my dear students, that the carbonyl compound, they undergoes the nucleophilic addition reaction. Carbon being less polar or less electronegative than oxygen acquires positive charge, and that is why the nucleophilic attack takes place on the carbon. The carbon in carbonyl compound is sp2, which simply turns into sp3, and the planar compound, after addition of the nucleophile, it turns into the tetrahedral intermediate. Oxygen acquires the alcohol or proton and turns into the final addition product that contains the hydroxyl group as well as the nucleophile bonded with the carbon. Here, my dear students, if we look at the reactivity, due to two reasons, we realize that aldehydes are more reactive than ketone. First is the steric reasons, that ketones have two bulk group, whereas aldehyde has got only one bulk group, which facilitates the attack of nucleophile. At the same time, the alkyl group, if they are present, then they are electron donating group, and that is why the electrophilicity of this carbon is more supported in ketone, less supported in ketone, because by donating the electron, these two alkyl group make it more negative. But if we have one hydrogen here, then the positive charge on carbon become more strong, and that is why the nucleophilic attacks become more stronger. Ultimately, aldehydes are more reactive than the ketones. But if we have the benzaldehyde or we have the aromatic aldehyde, then remember that aromatic aldehydes are less reactive than the alkyl aldehyde or aliphatic aldehyde or aliphatic aldehyde. So aromatic aldehydes are less reactive than the aliphatic aldehydes, my dear students. Then we have started studying about the addition of various compounds, that when HCN, see HCN when reacts with OH minus, which comes from the base, it gives us CN minus and H2O. This Cn minus, whatever we have got, it attacks on the carbonyl group. This Cn minus attacks on the carbonyl group and gives us the product cyanohydrin, which has both cyanide group as well as a hydroxyl group present. So methanol give methanol cyanohydrin, ethanol give ethanol cyanohydrin, benzaldehyde give benzaldehyde cyanohydrin, and acetone gives acetone